All right, well, here's a few news stories. The Ingenuity helicopter on Mars the flight has been delayed about a week because they need to update the software from Earth, which is apparently Linux-based. And in fact, Dan Tentler said he thinks maybe it's running Android. I don't know. But anyway, they found a software flaw, and they're uploading the firmware from Earth. So that sounds like pretty awesome. And so it'll be like a week before it takes off. The bandwidth, I think, is, of course, very low. So Ted Nugent, the old rocker, has apparently one of the COVID-19 complainers, and his complaint is that why are they having all these lockdowns for COVID-19 when they didn't have any for COVIDs 1 through 18, which I think Donald Trump said the same thing. He said, why do they call it 19? What happened to the first 18? And of course, it's COVID-19 because of the year 2019. But anyway, that's made him into the laughingstock of the internet for a while. So everybody is opening fast. Salesforce, the number one employer in San Francisco, is opening up very soon, next month. Although they're going to let people continue to work from home till the end of the year if they want to. People who are vaccinated can come into work, and I think there'll be lots more of this. The college just sent me the first draft of next semester's schedule, and it said remote on all my classes. But I certainly hope the college opens up face-to-face. But they haven't officially made any announcement yet. They haven't updated any of the COVID information on the CCSF website since February. But I don't even think it's very much up to the college administrators. I think it'll just be following the lead of the mayor or the governor. And the governor's already said the whole state should just open in the middle of June. So, and San Francisco K through 12 opened up today, a lot of it. So I really think the college will have to open for the fall anyway. This is pretty amazing. This guy runs a Spanish restaurant, and he gets unexpected food from the sea. And so he found this stuff called seagrass that nobody's ever thought of as edible. It has little seeds, which are like grains, like wheat, and he found it is edible, and it even makes a fine food when properly treated. And so he's made a little farm, a patch of like half an acre of ocean growing this stuff, and he's expanding it to like 5 acres. And that would be a new food source, and probably even more important, this stuff is the number one way to fix carbon out of the atmosphere. This stuff is only 0.1% of the ocean mass, but it fixes 10% of all the carbon that's absorbed by plants on Earth. So growing this stuff would probably be a lot better to get the carbon out of the air than any other technology that's known. So this may turn out to be a real growth industry. I mentioned before, a lot of long-term future thinkers have said if you want a real career that's going to be solid for the next century, you should get into carbon sequestration technology. We're going to need a lot of high volume technology sucking carbon out of the air. And this looks like a pretty good candidate. So the NASA is working on some real long-range tech concepts that are wonderful, like out of science fiction. The Arecibo Observatory in Puerto Rico is broken, and I think they're planning to rebuild it, but it'll be a while. But you could do the same thing on the moon. You could build a giant radio telescope in a crater. That would be pretty awesome. There are a lot of other ones. They want to do a neutrino detecting mission. The way we detect neutrinos now is by getting a vast amount of water or some other neutrino collecting substance and putting it deep in a mine to try to protect it from all the other sources of radiation, to catch a tiny amount of neutrinos here. But you could just put a satellite closer to the sun and measure the information about the neutrinos. And then you learn more fundamental physics and more about the inside of the sun. And there's quite a lot of cool ones here. They want to set a swarm of spacecraft into Venus to fly around and measure the Venusian atmosphere. They want to land on Pluto with using what atmosphere it has. They want to set CubeSats with solar sails to sail around, powered by the solar wind to travel through the solar system and interstellar space. And just a lot of really great sounding stuff. It will be fun to see progress on those exciting things. And this one is pretty incredible. As I'm sure you know superconductors are wonderful. They have no resistance at all. They make it possible to make fantastic electronics and fantastic magnetic devices. But the problem is that they're very expensive to operate because the superconducting material has to be cooled down to near absolute zero. But what these guys have found is you can make materials superconducting briefly by just hitting them with a laser. And this lasted for only a pathetic amount of time, like a picosecond before, which is enough time for light to move a millimeter or something. But now they managed to make it 10,000 times longer by having a different type of laser. So this might be a way to make warmer things. Perhaps, I don't mention the temperature here, but I don't imagine it's up to room temperature yet. But this might be a way to make superconducting things at room temperature. There's a couple other ways to do it, but they're all extremely limited. But if we can get a room temperature superconductor, it would open another whole new world of electronics. And quantum computing. Many things can come if we had superconductors at room temperature. This is the first I heard of this today. 3 American states have stopped using Johnson & Johnson because it has, some people have reactions. 8 people experienced adverse reactions. So in any case, it still sounds like a really small risk, like 1 in a million. This reminds me of the AstraZeneca, which is not used in America, but it was the same thing in Europe. A very small number of people, like 1 in a million, would have a bad reaction. And so anyway, that's an interesting statement. And they ran out of Johnson & Johnson anyway in America because they had a problem in the factory that made it. So I don't even think you can get it anywhere around here right now, but 3 states have decided not to use it anymore. I don't know. I think America has enough vaccine of the other types. We could just quit using J&J here if we don't like it, but I guess we have to wait and see if there's really something significantly wrong with the J&J. Yeah, here's the schools that are opening up for learning today. And it's a lot of them. Heard a funny beep. I guess it's somebody trying to, some kind of message coming in. I think it'll have to wait. All right. That's one thing about my computer. It beeps when a message comes in, but it doesn't actually open the app or tell me which app is sending a message or anything, so it's not very useful. But you see, a lot of these schools are opening. So I really think San Francisco is opening schools and everything else opening very fast. Colleges want to open, but they're trying to decide, like everybody else is, whether to require vaccinations. This is hitting the press and the political discussion as the issue of vaccine passports. I think it's complete nonsense, personally, because a large number of people refuse to get the vaccine, so you can't require it, and the vaccine is not even approved officially. It's only for emergency use, and it's not even available to everybody, really. And also, when you do get the vaccine, you don't get any real proof. You get these ridiculous vaccine cards that look like something you made up on your home printer. They don't look official at all. They'd be easy to forge. The blank Word documents to print your own are available online. Anyway, so some colleges are trying to require it. Other colleges are not trying to require it. We'll see what happens. I highly doubt that any of this vaccine passport is going to be enforced by anybody much in America in the near future. And so this one I thought was very interesting. As you probably know, I'm very, very opposed to cryptocurrency. It seems to me like none of them are worth anything. They're all just a stunt. And the new thing is non-fungible tokens, which are also just a complete fraud with no actual value. And this one here is even funnier. They will let you buy shares in celebrities, although the celebrities don't know that they're being sold this way. And the idea is just they'll be bought and sold based on the fame of that celebrity, and that will cause the price to go up and down, and people will pay for it, even though you don't get anything. You don't get a statue of the celebrity or any special rights to one of their songs or anything. And then it turns out that on top of that, it's not even a cryptocurrency. It's just running a normal database on a database server. And it's not, it's a cryptocurrency that cannot be converted back into dollars. You convert your Bitcoin, money into Bitcoin. You use Bitcoin to buy these special cryptocurrencies for BitClout, and there is no way to sell it. The only way to get your money back, like if you buy some celebrity and then the price goes up, how do you get your money out? The only way is you go on some third-party market and you offer to dump your tokens, and you have to sell them at like 10% of their real value because nobody wants it. So this is what they call shitcoins. This is completely fake crypto. I mean, all cryptocurrency and all blockchain projects are essentially frauds, but there's ones that are even more fraudulent than the rest. And those are the ones they call shitcoins, and that's what this is. Anyway, people try to buy shares of high-priced collectibles, and of course, it's, well, I mean, I guess you could buy shares of the Mona Lisa if they were somehow limited, and it might make some sense, I don't know, but this, you're buying all NFTs, you're buying something with a celebrity's name on it, and there's nothing else to it. It's very strange. And, what it shows, I think, is there's an awful lot of people with money, and they can't figure out what to do with it, and they're just throwing it in random crazy things. Anyway, that's enough of this, I think. We'll go on to the official stuff. This is 127, and today I want to talk about 64-bit assembler, which we've already talked about a bit. And, all right, so I've got my slides here, and I'll bring those up. And it's not in the book, but the slides are on my website. And I'm going to bring up my virtual machine so I can demonstrate it. I'm not sure if that's really going to be necessary, but it'd be a good thing. I'm just using a Debian 10 virtual machine, the same one you'll make if you're following the projects. Debian 9 is just the same, I think. And you probably could do it all in Kali too if you want to, but I've gotten pretty fed up with Kali and I'm sticking to Debian pretty much. Let's see if I can get in this machine. I got to find my IP address. All right. 192.168.11.7. And I could type right in the terminal, but as I mentioned before, I don't like doing that because then you can't copy and paste, and it's just for the birds. So after I got used to using cloud machines, I just put SSH on all my Linux servers and treat them like headless cloud servers, and that suits me better. All right, so this is my view into my Linux machine. All right, so in a 64-bit machine, you have 64-bit registers, and you have a lot more of them, like 16 of them. There are a lot more registers, and each one has a lot more bits. And so there they are. And this line here indicates that the first bunch, A, B, C, D, base pointer, stack index, destination index, these you can split in half. You can even split in smaller chunks to refer to 32 or 16 or 8-bit portions of them, because those are the registers that also exist in 32-bit processors. All right, but normally you use an R now instead of an EAX. You have an R, IP for instruction pointer, RSP for the top of the stack. All right, so you can refer to in fact, you can do it with these other registers too, although they don't map to 32-bit registers. You can refer to lower 32 bits, lower 16 bits, and lower 8 bits of these registers. So you can refer to smaller portions of them if you want to, but most of the time you just work with the 64-bit register. Now, this is kind of nuts. I felt sort of ripped off when I learned about this. Windows does not implement 64-bit addresses. I don't know why. They only use 48-bit addresses. So that means you can't really get to 2 to the 64 bytes of RAM. Now, of course, that's a monstrous amount of RAM. More than that would be 16 billion bytes of RAM, and nobody can afford that much, so there's no real need to have it all. Anyway, so that's what happens. But this has the unusual result that you have 2 blocks of memory you can refer to at the ends, and the memory in the middle you can't reach. And so here's more information about how much RAM you can have in various versions of Windows. Internal limitations in Windows, in addition to the limitation coming from only using 48 bits to refer to the addresses. So with 48-bit addressing, that means you've got high addresses here, starting with FFFF, then in a whole dead zone in the middle of illegal addresses you can't use, and then a low bit where all the addresses start with 0000. That's the game, and this is where kernel mode goes, and this is where user mode goes. And you could have 48-bit addressing, you could have 56-bit addressing, and if you really had 64-bit addressing, then you'd have all of it, high half and low half, and this would be the 16 billion bytes of addressable memory. The 48-bit limitation comes from the size of the physical address that comes from the pinouts on x86. Yes, thank you. That makes sense. Anyway, so all right, so you don't use int 80 anymore in 64-bit. You just use a command called syscall. And then you can call system call, and it works very much the same way. You use registers to pass the arguments, and you pass the number of the call in RAX. You don't use the stack at all. You use registers. So there's a table online where you can look up the syscalls, and they're still, some of the simple ones are still consistent. 0 is read and 1 is write, and on you go. So it's not that different than what we've done before with the assembler. So there's an online zone explaining it all here, explaining all the various registers, and there are 80-bit floating point registers and 128-bit, I think, floating point registers. I'm not quite sure. There's a bunch of registers around in addition to these, but these are the only ones I worried about, the simple integer ones. And so here's the opcodes you see in 64-bit instructions. They're very much the same. Move, exchange is one I don't remember seeing in 32-bit code. Push and pop, add, divide, increment, negate, NOP is still there, and so on. You have all the usual kind of instructions. Linux would have the same limitation on the same hardware. At least the 48-bit would be the same. Those other limitations, the ones back here referring to Windows versions, are beyond the fundamental 48-bit limitation. So these would be different. These are software limitations inside Windows in addition to the 48-bit limit. But the 48-bit limit would be the same on Linux, yeah. All right, and there may be other limits inside Linux for all I know. I've not seen a chart saying how many bytes you can actually use in Linux. I assume it gives you the full amount of the hardware capability, but I don't really know if that's true. So you can make programs here. You have to install YASM. I did, and so here's a simple program. It's very much like the simple hello world that we've done before. Wonder if you could hide things in those illegal spaces. That's right, it's a hardware issue. No, you can't. You can't address that memory. You can't use that memory, and it's not there. Yeah, that's an issue. I know, that would be interesting if you could hide something there, but I don't think there's any convenient way to do it. Now, you could perhaps, now what you could do is you could do like what Bloomberg tried to pretend the Chinese did. You could add extra hardware to some device beyond the standard hardware, and then you'd have some extra memory to point to that standard programs wouldn't know about, I guess. But unless you modify the hardware, I think there's nothing there. Anyway, so this is what you do. Here's a 64-bit constant in RAX, which is A, B, C, D, E, F, G, H. So here's how you make a syscall. You push RAX onto the stack, which I'm thinking might not be necessary. They say no argument goes on the stack. You know, all right, I'm glad I'm ready to do this demo. I got this code from someplace, and now that I'm looking at it, I'm questioning whether this code is necessary. Anyway, then you put the length of the string, the address to the string. Oh, I see. Okay, now I get it. I put the string on the stack, and this is the address to the string. So these are the parameters going up onto the stack. Okay, this is the syscall number. Now I put this in RAX. Okay, so this is right. So I move this into RAX and push it onto the stack, and then I'm done with RAX. Down here I set RAX to 1 and RDI to 1. So that will do a write to device number 1, which is standard out, and then I make the syscall. So you have to do YASM to assemble it and LD to load it, and then when you run it, you get the string, and then you get a seg fault because we didn't actually exit properly. It just stopped. And the string is backwards, which shouldn't be much of a surprise. After this class, you know that strings are loaded in little endian order, so they'll come out backwards. You have to actually put it in the other way. So to get the exit, we're going to have to use syscall number 60 to do the exit. So to fix that problem, we load a 60, which is 3C, 48 plus 12. And then make that syscall, and now it prints the letters backwards and then doesn't crash. I didn't put a carriage return. It's just got these 8 characters and nothing else, but it doesn't crash anymore. It now correctly calls exit. And so you can put the letters in order by just reversing them here, and now you got them forward and a proper exit for what it's worth. All right, and if you want to include the carriage return, you want more characters, so you could now use a data section in addition to the text section. You can define bytes. You can just type in strings. characters, which are interpreted as ASCII 1 byte per character, you can put in numbers. 10 is line feed. And then you can just count the number and load it in here. I put in the pointer to the string, and then I counted it up to 13 myself. And then you can call this, and now it will print hello world. And this one will print hello world and then put a carriage return at the end. All right. So you can use object dump to look what's in there. It'll tell you it's a 64-bit assembly code, and it'll tell you where it starts. Notice that 64-bit code, just like 32-bit code, likes to start at 400,000. Remember, we said in Windows, all the Windows programs think they're at 400,000. And you can get the symbol table down here and see where it is. Here's the starting address, which is 400,000 in B0. Here's the basic stack segment. And there you go. Here's the text section at 400,000 in B0. Here's the data section at 600,000 and something. So you can see what's going on there. So you can use GDB, which you also had to install on my Debian. And if you do info proc mappings, you'll see the same thing. When I loaded it on my new Debian 10 running locally, it didn't load the second section at 600,000. It loaded it at 400,002. 402,000 and 400,000 are the two segments. So I guess the loaders are different on slightly different versions of Debian. But you notice it has two sections here labeled exactly the same, which is a little rude. You can't tell the text section from the data section. But this is just a defect of GDB. GDB doesn't let you see that. There are other ways to see it. One simple way to see it is to just disassemble start, and that will show you that the start is at 401,000. So that is in the first section here, right in the middle. This goes from 400,000 to 402,000. So this is apparently the text section. And this must be the data section, 402,000. And indeed it is. If you dump the 402,000, you see right there, HELLO world, that is the string there. So that's how it was laid out by my loader on Debian 10. And different versions of loaders and operating systems will load it in different ways. All right, you can do info registers, which you can abbreviate IR the same as you can in 32 bits, and you'll see here's all the registers. There's more total registers, but the same general idea. The 64-bit values are kind of longer, but there they are. Notice the stack pointer is at these high values, 7FFFF. And the code is here, so I'm thinking I must have been wrong, thinking it was kernel and userland. Oh no, this is still userland. The kernel would be, no, I'm still confused. They're all starting with zeros. Yeah, okay, I'm not really sure what part of memory would be for the kernel. I thought it was one of those two segments, but it looks to me like here I am in one segment and here I am in the other segment. They're both being used by the same program, so I don't think it's that simple. Anyway, there's the instruction pointer at the start, and there's the stack way up there. All right. So you can use read, for example. Read is just a syscall 1 is write, and syscall 0 is read. So you define a string just to have a placeholder. I'm just going to put junk in there to reserve space for 10 characters and another character at the end. And now I can set a pointer to the start of the string and then read from standard in. So it's going to read into there. Then I can write and print out the answer with 10 bytes, and off you go. So this means I'll be able to put in apple, and out will come apple, and then, since I didn't put in a null byte to terminate it, it will just have whatever is left over there, BBCC, and then the null at the end. So that's pretty sloppy reading and writing into a string, and obviously it's got a buffer overflow vulnerability instead of in addition to all its other defects. But you can now make a sleazy Caesar cipher. You can reverse space for 8 characters. Now you can point to the string, and I'm going to read the string here. So I replace this placeholder with the string I wish to encrypt. Then I'm going to add, since I'm only doing an 8-byte string, I'm just going to add 1 to each one. I'm making a Caesar cipher that moves everything forward by 1. And I'm so sleazy, I'm not even going to worry about the fact that the Z is not going to wrap around to A. I'm just trying to make the simplest, very limited Caesar cipher. So I add a 1 to every byte. Then I just print that out. So that sounds pretty good. I put the contents of the string in RCX. I added this number to it, and then I put it back in where it came from. So I overwrote that with all the letters moved forward by 1 in the alphabet, and then I print it out. So this should be a assembly language Caesar cipher. And if you run it, I give it hello, and it changes. It takes H to an I, the E goes to an F, the L goes to an M, and the O does not change. And I still have those extra bytes left over. So it only changed 4 of the bytes. And if I paid attention when I compiled it, it warned me here, the value does not fit in 32-bit fields. See, this is the problem with assembly language. I wanted to do a 64-bit add of this immediate 64-bit constant to the 64 bits in this register, but it turns out that that command does not exist in Intel 64-bit assembly language. A lot of things you might want to do, that command does not exist. And the assembler, instead of just crashing, it replaced it with a 32-bit immediate adding here, and then warned me I wasn't able to really do what you asked for. I took the immediate value and interpreted it as 32 bits instead. So if you look at object dump to look at your code, you'll see that what it really did was add the 32 bits to that value instead of the 64 bits. And that's why it's only changing 4 of the characters. So that's the thing to know. Where was the Caesar cipher 3-letter shift? This one just does a 1-letter shift. If I wanted to do a 3-letter shift, I'd have to put 030303 here. That's all. This is just a 1-letter shift Caesar cipher. The simplest thing I could think of just to get started. Good? Very good questions. All right, and if you want to know why, you can go into the architecture manual, which is available online, and then you will see you can add a 64-bit register to a 64-bit register, and you can add 64-bit or memory 64 to a register, but you cannot add an immediate value. Immediate values are here. You can add an 8-bit, 16, or 32-bit immediate value to a register, but you cannot add a 64-bit immediate value to a register. You don't have that option. You know, all the commands in the processor are hard-coded in the layout of the silicon. You're stuck with whatever the Intel developers give you. So, if I wanted to fix it, then what I'd have to do is read the data. Then here, instead of trying to add this directly to it, I would take the existing word, put it in RCX, then I would take this 64-bit constant and put it in R8, and then add R8 to RCX. Now I can add 64 bits because it's register to register, and then I can take the result and put it back in. This will move all 8 bytes. And by the way, you really might as well get used to this because we're going to get to ARM pretty soon, and you have to do this all the time in ARM. ARM has almost none of this direct referring to memory stuff. The way you do everything in ARM is load everything into registers, do the math in registers, and put everything back into memory. So you do this kind of thing a lot. So it takes several commands to add up to what you might imagine would be just one operation. So that one will actually work. Now I can give it hello, and it changes all those characters, including the P. And then it still has a couple of characters left over because I still didn't fix the problem that I didn't put a line feed or anything out here or a null byte to terminate the string. So it's a pretty sloppy Caesar cipher, but at least within the limitations of my design, it can do 8 characters. All right, and so I just gave you a couple challenges to solve here. And you can write a few programs to solve a few of these in the 64-bit programming assignment, which I think I'll just point to now since it's essentially this lecture is just following it. So if you want to do this, it's here, Intro to 64-bit Assembler. And so it explains this. You set up the ones I just did for demonstration, and then you have some challenges here. So there are some challenges at the end where you improve the Caesar cipher. Down here, so make a bit. Now you do the Caesar cipher 3 spaces instead of 1, and then you make a loop here and fix it, and then you fix this thing so that it prints the word good, even though the string has bad and good. So there's a few simple challenges there to finish partially completed assembly language in 64-bit to get you started. All right, and now I think we're down to the cahoots, which I've got here. This one here. And here, all right. Line feed, but not a carriage return. Yeah, you could do both, but the carriage, that's right. That one you saw line feed, but not a carriage return. That's why it went down. Yeah. All right, guess we're ready to go. All right, so how many bits in AL? Yep, 8 bits in the AL is just the lowest 8 bits of a 64-bit register. All right, how many bits in that RAX? Okay, that's 64. By the way, you know that question about the line feed, I think it read the line feed for me when I typed in Apple line feed, it put the line feed in. But I'm not quite sure. It would be fun to stick it in a debugger and find out why that line feed ended up there. Anyway, 64 in the RAX register. The ones starting with R are the full-size 64-bit registers. All right, so how many bits does Windows use for addressing? Okay, that's 48, like we talked. It doesn't use all 64, but of course it's got to use more than 32 or there'd be no point. 32 is what you get, of course, with a 32-bit machine, and then you're limited to only 4 gigs of RAM. All right, so if you don't have an add immediate command, what do you do? That's what you do. This is what your compiler always does. One line of a high-level language like C might be a whole bunch of assembly language commands. You use several commands to add up to what you want to do. All right. All right. I know who that is. And I think I know who that is too. All right, good. So I'm going to stop